We'll try
Yes.
to complete it.
Yes. So I think, yeah, good. So Ritesh, do you know Abhik? Abhik Roy, he's here. He has joined. Ritesh? Yeah, no problem. Good morning, Abhik.
Good morning, sir.
And there are so we can keep admitting, I think, some unless we get too close to the top limit, and by then we don't have to keep people waiting in the waiting room.
Sir, yesterday I noticed there were around 150 participants in total. Even in so we have limit till 300. So I think
yeah,
we can enter at least.
So we can accommodate most of those who are in the waiting room. So
Around 50 were there on YouTube. I checked.
Yeah. So who is taking care of this, Abhik? Is Ravi there or Satish?
This is Sairam, sir, from IT team. Arun Sairam.
Sairam, very good. Good morning, Sairam.
Good morning, sir.
So thank you very much for all the support you all give, Sairam. Because
thank you, sir.
Sir,
it's one
great.
request, sir. So, to whom I have
Yes.
to admit and I have to make a co-host, sir. That list I don't have.
Yeah, make of course the speaker, which is Sanjay Majumdar. Then I will be a co-host. Dr. Ritesh Gangwar will be a co-host.
Okay, sir.
Okay, and then if Arijit or Sunil join, please make them also co-hosts.
Okay, sir.
Then I think we are good with that.
Okay, sir.
Sir, I think if Salvi joins, she will also need to be a co-host because she needs the Salvi. So she needs the microphone access.
Correct. So Abhik is there are a few student coordinators who are helping us with the question answer session. Sairam.
Okay, sir.
Yeah,
I'll make them as a co-host.
Yeah, so Abhik is one of them, and Salvi. Salvi is joining from Austria. So it's very early morning for her. So when you see her, she is Sunil's student, as you know.
Yes, sir. Yes, sir.
So please make her also a co-host.
Okay, sir.
And enable the chat for everybody so that people can post their questions.
That should be enabled for everyone.
Yeah. And somebody needs to keep an eye on this Zoom bombing annotations by participants and so on. So I think I was told yesterday that only the speaker can disable that.
Yes, sir.
And if that is the case, then I think some of you have to keep watching it. And if you notice anything, then you have to call Sanjay Majumdar immediately and tell him what to do. He may or may not know. Do you have Sanjay's phone number?
No, sir, I don't have, sir.
Yeah, I think you should have it. Just in case. Okay. This is Arun Sairam, right? Hello?
Yes, sir. Yes, sir.
Arun Sairam. So I have your number with me on my WhatsApp, and I'm sending you Dr. Sanjay Majumdar's contact on WhatsApp. You should have it now. Got it?
Yes, sir, I got it.
Very good. So keep that handy. And I think we have a comfortable margin so we can admit people as they enter the waiting room.
Yeah. I'll start. I can also do so. I will also do so because it's a progress. So.
So Ritesh, who is making breakfast these days? Anil, Jankiram, or who is it?
Both.
Both of them are there?
Both of them.
Okay. Good.
That way I'm blessed.
Yeah, I know you have an attached kitchen.
I think one of the best things living in KCR for me.
Yeah, I also enjoyed it for a long time.
Yeah. They had to close for some time during.
Yes, of course.
I think professor is also joining us now.
Oh, Sanjay has joined, I think.
Yeah.
Good morning, Sanjay. Sanjay, you can unmute yourself. And you also have to start your camera, I think. Very good.
Yeah, we can see, sir.
Yeah. Good, Sanjay. Good to have you back.
Yeah.
Very good morning.
Morning.
Morning, sir.
Good morning.
Sanjay, Ritesh is with us today. Ritesh Gangwar.
Good morning, sir.
Good morning. Good morning.
Yeah. So Ritesh will also be helping us with the question answer session and
So he is in
through the
physics
meeting.
department or?
Sir, I'm in physics department at IIT Tirupati.
Ritesh is currently the head of the Department of Physics at IIT Tirupati. Yeah. Ritesh is directly my boss.
Sir, now you are exaggerating the facts too much.
So what is your field?
Sir, I work in AMO, this atomic molecule.
Call me Sanjay. So like we don't call it
So, but I work in AMO and also plasma physics.
Oh, great. Okay. So condensed matter, AMO, and plasma physics.
Not condensed matter that much. I don't work in materials, but spectroscopy do. Spectroscopy, plasma, and AMO. So AMO I link through plasma through spectroscopy because it involves cross-section calculation and other things.
So Ritesh has a very wide background in pure and applied sciences, theoretical as well as experimental methods. So I think it's a very rich background.
I did my PhD at IIT with Professor Srivastava, Rajesh Srivastava.
Oh, IIT Roorkee.
IIT
Yes.
Roorkee.
Ah, they have published a recently nice paper. Did you see that? I think some C3 or some, it's in PRA. I saw just. Bindi Arora, Rajesh Srivastava. And,
Yeah, I think dispersion relation on
relation. I just saw yesterday.
Yeah. So Sanjay, do you want to check your screen
yeah,
sharing?
I'll
Because
yeah,
I think we will start in another 3 minutes.
I'll just check it.
Yes, we can see your screen, sir.
Yes, very nice.
So maybe let me.
Oh, I know what you're showing there. It's a great image.
Coming to the screen now.
Sir, you might need to change, in slide. Yes. Yeah, perfect. Perfect, sir.
Yeah, I think we seem to be all set. We have another 2 minutes.
Maybe I just. Actually, this week, one of the students, this means tomorrow. This is Viva is there. Next
Oh.
week, one more is there. So all together came.
Great. Yeah, once you get into academics, it is a 24/7 involvement.
Yeah.
Spouses don't like it.
Sir, problem get exponentially increased when both are there with the same profession.
True.
Oh, is it yours?
Yes.
So in my case, it's
Yeah.
like more complicated.
Yes. Yes. But they don't like each other's.
Even in the field.
That remains.
No.
I avoid physics discussion at home.
So, Sanjay, it is time. Do you
Right.
think we should start?
Right. I think whoever is there, I think.
Yeah.
will be in
So, yeah. So, good morning, everybody. We are now quite well into the subject, and we are having the third lecture this morning by Professor Sanjay Majumdar. He is now very well known to all of you. And Sanjay will be delivering the third lecture in this short course series organized by CAMOST. Sanjay, I think there is some annotation going on your screen.
Okay.
Yeah, so just keep an eye on that, and I think you need to disable that.
Remote control.
Yeah.
So I have
Sir,
to,
on top
Sairam?
of the screen, that option will be there, sir. There you can disable attendee annotation.
annotation disable. You can make it.
Yeah. I think this is called Zoom bombing or something, right? There is some term for this.
Yes, sir.
We
But
have
then,
to do something. Okay. Nothing is disable. Erase, format.
And participants come and they can draw some lines and cartoons and pictures or just scratch. the image. That's what somebody seems to be attempting for whatever joy they get.
So I don't know how to stop it. I think Sunil knows.
Yes, Sairam, can you please help?
On top, middle of the screen, on top, there will be a more option will be there, sir. The stop sharing, that option was there as a middle of the screen.
Middle of the screen, what is there?
Stop sharing option on middle, on top of the middle.
Stop new sharing is there. So no, not a stop.
On last, there will be a more option will be there, sir. With the three dots.
Right.
If you click that one, disable attendees annotation option will be.
All right. Fine. Thank you.
Got it?
Yeah.
Okay, good. So I think it is now done, and we can people can bomb, and their bombs will not explode, I think. So we will continue with the lecture. We have today Dr. Ritesh Gangwar to help us. Dr. Ritesh is currently the head of the Department of Physics at IIT Tirupati. So welcome, Ritesh, and Ritesh will help us conduct the question answer session. So let me invite Sanjay to please continue his course. Sanjay.
So should I start?
Yes, please.
Good morning, everyone. So let me just welcoming you. I think all of you have attended my last two sessions. So those who are new, or you can refresh your memory just by see that let us recollect what we have done. So far we have discussed that we can confine the light in a small volume, and then what would happen that sometimes small volume is known as cavity. Okay, it's popularly known as. Then we can quantize this. So this is like a small volume which you see it here. We can quantize the light if it is confined inside this volume. Okay, and here we have discussed only for the single mode, so that you can extend it to the multi-mode. Okay, but I think we will not be able to go because of a time shortage. Okay, but enough. I think that if you have a single mode knowledge, you can extend it for any other multiple or two modes, or okay, like that. So what we have achieved that once the light is confined, what we achieved that we will get that different focus state. Focus states means that these are a number state which we discussed, okay, and also popularly known as a focus state. Like here you see that there is a zero state, first state, first excited state, second excited state, like that. So this means that there is no photon there. First excited state means that there is a one photon there. Two is there means that there is two photons are available. Okay, like that you will get infinite number of quantized state or number states. Okay, which are known as the focus states also. So if we have if you have the states like that, and they are the eigenstate of the Hamiltonian. Okay, so what you can have that you can tell easily that they will form a basis. All the number states can be form a basis. So you can have n equal to 0, 1, 2, that form a basis set. And in the vacuum, what would happen that at n equal to 0, what we saw that the number state, okay, which will also known as vacuum state at n equal to 0, it has a minimum dispersive nature. Okay, that we have proved it. We have seen it, the feature of this, or you can say that it is also a minimum uncertainty state. So that is because that standard deviation of this vacuum state for the canonically conjugate operator, okay, Q and P, their values are same, and it is square root of h cross by 2. And if you multiply these two, which will give you the uncertainty relation, so you will get h cross by 2, and which is the minimum limit for the uncertainty, Heisenberg uncertainty relations. So we have realized, also understand that there is a lot of advantage if you work any experiment using this minimum dispersive state. or the state which is at the ground state, what we are talking about, because of the spread of the dispersion, okay, is minimum here. Once we understood this one, let me just go to the next slide. So, yeah, let me just. So now the question is that, okay, so we got a very good state which is having the minimum dispersion. Is it the only state? And there's a disadvantage that this is the state where there's no photon. What will do that? That if there's no photon, how can I interact with the matter with this? Okay, so that is not a wise to only have this vacuum state. So it is better to have some states which is satisfying the minimum uncertainty relation. Also, it has sufficient number of photons. So is there any such a state? That is a very, very valid question which was raised in the ITs last century. And J. Glover got Nobel Prize to answer that. Okay, so he has proposed a new state which you can see that which can be constructed, okay, theoretically exploited. Okay, so that is known as coherent state. So already people know that from the simple harmonic oscillator, okay, there is a possibility to make the coherent state. Okay, and if you are really interested, you can look at that book by J.J. Sakurai, Modern Quantum Mechanics, where in case of simple harmonic oscillator, it has been discussed thoroughly. We'll also discuss, but we'll not do many derivations. We'll try to avoid. Okay. By the way, today there will be a tutorial session, so many of the derivations will be done there, or some of the assignment which you have got. Okay, it will be discussed there. Anyhow, so what is this quantum coherent state? Now, I think you know from the classical point of view, what is the coherence? Let's give an example. Suppose I'm assuming that you are a student staying in the hostel. So if you and your friend, okay, started from your hostel, let's say that you are having a distance between you and your friend as x. And when you reach the department, okay, you still have the same distance. That means you are actually keeping your distance between you and your friend is intact over a length from your hostel to your department. So you are coherent in that sense to that distance which you traverse. So it will be having, if you can say that you are coherent and the coherence length will be the distance between hostel and the department. Similarly, okay, if you keep some setup, experimental setup or some substance, and if you just wait for some time, and if you still see that, okay, the system is as it is, it doesn't change the phase, it doesn't change the structure, okay, then what do you say that the system is coherent over the time. So we'll get coherent time, okay, for the systems. So what does it mean? Means that we are not able to change, or system is not changing its phase, structures, its properties over time or length. Okay, so then we'll say that classically it is coherent. Can we say similar thing here? Yes. Okay. So what actually does when you have an experimental setup or some quantum substance? Okay, it will be exposed to the environment. That means that environment will perturb the system. And when the environment perturbs the system, we can write that as a perturbation Hamiltonian. And perturbation Hamiltonian, you can write in terms of the canonical conjugate operators, the P and Q, isn't it? So this P and Q, again, you can in turn write in terms of the creation and annihilation operator. So ultimately, that if a system is kept somewhere or it is traversing some distance, what actually you understand that it will actually go through many creation, many operation of creation of annihilation operator on the system. So that means that if after getting operated by the creation and annihilation operator, okay, if your system still survived as it was, okay, then we can say that the system is coherent. So this is intuitively we'll prove it. Okay. So what we can say that, let us say that we'll define this coherent state quantum mechanically, that when we'll say that the state psi is the eigenstate of the annihilation operator. That means that when you operate the annihilation operator on the state, okay, the state doesn't change. That means you get back state as it is. So what you will have that you will get an eigenvalue corresponding to this eigenvalue equation. That is like eigenvalue equations, okay, where A is the operator, okay, operating on psi will give you eigenstate psi back, okay, and you will get eigenvalue. So psi becomes the eigenstate of the annihilation operator, okay, and certainly that since annihilation operator is not Hermitian, you expect that this is a complex value system, where that eigenvalue is complex value. Okay, so what would happen that if we get this kind of a state, we are just proposing that psi, which is the eigenstate of the annihilation operator, okay, that will be as a quantum coherent state. We'll prove that whether really it is coherent after some time also. Okay. Before that, let us dissect that what are the possible form of the psi. Okay, so to our disposal, already as we have explained that we have the basis set, okay, which is coming from the Fock state or number state. Okay, so that is n states are there. Can't we form any state out of this? Okay, any state means in the system. Okay, out of this from these Fock state, that is n state. So what we can do that we can write the psi in terms of the linear combination of the Fock state. Okay, so what you see that we have written summation over n Cn n. Okay. So Cn is the expansion coefficients that will tell that contribution of different Fock state on psi. So square of the Cn will give the weightage. Okay. Now people have worked on it. Okay, they found that what is the expression of the Cn. So Cn, it was found out if we have some kind of a variable which is complex in nature, alpha, and if we can write that psi is a summation over n alpha to the power n by square root of n factorial of on the n, that number state, okay, then what we can see that we have to prove it. I'll not prove it here, but I'll advise you to work it out, that you will see that this will form a eigenstate of the annihilation operator. And here n is a normalization constant. Okay, so what we say that psi equal to 1, which will give you n is nothing but exponential minus alpha square. So since alpha is the complex quantities, okay, square by 2. Okay. So here alpha is at any, here as you see that alpha is any kind of a complex number. It can be real, it can be a plus ib, any kind of a complex form. Okay. So as long as it is scalar, okay, that's sufficient. Okay. So I would just leave this proof, okay, that if A operating on this expression of the psi, okay, where we are expressing psi in terms of the number operator, number states, okay, we'll get back, okay, we'll get back the state itself. And interestingly, what you will get, that you will get eigenvalue as alpha. So what you got it, that A psi will give you alpha psi. So that means this psi, which we are parameterizing using the alpha, will give back the eigenvalue alpha. So in a short notation, and it is very widely used, instead of writing psi, people write this new state as alpha. And alpha Okay, I'll explain that. The form of alpha is nothing but this one. Okay, that you have a normalization constant, which is this one, and there is summation over the number of states. Now here, when you work it out, what you'll find out that you have to use a recurrence relation. Recurrence relation between the consecutive coefficients, okay, the C coefficients, okay. So Cn and Cn minus 1 will be related by alpha by square root of n. And if you just use subsequently, what you will find out that you can get the Cn in terms of C naught, which actually will be coefficient for the vacuum number state or zero number state, okay, by vacuum state, okay. And but the coefficient will be now, it will be alpha to the power n square root of n factorial. Okay. So now what you can find out, C naught certainly, okay, if you put that n equal to 0, okay, so this factor becomes 1, is nothing but your normalization factor. So C naught is nothing but your exponential minus alpha square by 2. So ultimately what you get, okay, you get that you can achieve the eigenstate of annihilation operator, and this eigenstate is parameterized by any kind of complex number, and you will get back that complex number as a eigenvalue. So what we can now make a notation that instead of writing psi, we are writing that new state, okay, the eigenstate of A, okay, annihilation operator is alpha, and we are getting alpha alpha. Okay. So it is easy to remember that what actually the parameter used to get the eigenstate.
Excuse me.
Right.
I think there's a question in the chat box.
Okay.
So it reads, what makes such a state coherent? Is there any property for which it can make any state? Okay. Is there any property for which any state is coherent?
Okay.
I can say
As
any
I
state is
said,
coherent.
intuitively that you could understand why the eigenstate of the annihilation operator is coherent. But now we are going to prove that okay, if you just leave the system over time, okay, what would happen? Whether you will get the system still as an eigenstate of the annihilation operator. If you see that state still is the eigenstate of annihilation operator after time set t equal to t naught, then you will say that, oh yes, this is the coherent state, okay, because your system is again that is a eigenstate of annihilation operator, and it didn't change. Okay, the phase also didn't change, nothing changed. We get back the same state back after time t. Okay, so just wait for a few minutes, so it will come back. So what actually you said, I am just going to address that, why it is called coherent. Okay, so that word why we have to understand by just varying the system over time. So we need to operate the time evolution operator on this, isn't it? On the alpha state. So once you have this, okay, we can use this time evolution operator. But wait, here there's a catch. Catch is that generally when you apply time evolution operator in any quantum mechanical systems, we generally consider the system is stationary. We operate e to the power minus I Hamiltonian times t by h cross. That unitary operator time evolution operator on this state from the Schrodinger picture and get the time evolution. But that actually required is that you have to have a stationary state. Okay. But wait, here what happened? Here the alpha, what we have just said, is actually linear combination of the number state. And as you see that, these number states are eigenstate of the Hamiltonian, but what happens that their energies are different depending upon how many number of photons are there at the particular state. So that means their energies are different. So you can't write the state which is a summation of a different energy state as a stationary state. Okay, so you can't apply this unitary evolutions, okay, what you used to do now it's directly. Instead of that now what you can say that you could apply this unitary evolution operator on the number state itself. which are actually stationary. So because the number state, their the energies are fixed. Okay. So what we'll do that, we'll say that the time evolution of alpha will be alpha t, where we say that our number state is evolved over time, okay, by using e to the power minus I h t by h cross. So here, as you know that the number states are eigenstate of the Hamiltonian will give you the quantized energy levels. So we can write En corresponding to the number state, and then we sum it up. So we can do that. There's no harm in it. So the advantage is that, sorry. So here that En is n times number energy of the photons. Okay. So energy of the photons h cross omega times n. So if your h cross get cancelled, and what you will see that you will get, okay, e to the power I omega t whole to the power n. And Cn, as you just saw that okay, that is it C0 alpha to the power n by square root of n factorial. So I just replace Cn by that C0 alpha to the power n by square root of n factorial. So ultimately what I get is C0 e to the power I omega t alpha to the power n by square root of n factorial. Apart that this is of, not apart, is the coefficient for the number states. Okay. Now just look at it. Do you recognize this expression? This is nothing but the same expression which you use as for alpha. Only thing that here you just replace alpha by alpha e to the power minus I omega t. Isn't it? So we just replace alpha by alpha e to the power I omega t, we get the same expression. So instead of writing alpha, okay, alpha t, what we can write it is alpha e to the power I omega t. So we got a new state, okay, of this format. And this format, as you said that, okay, if you write any state in this format for any kind of a complex scalar values of alpha, okay, we'll say that will be eigenstate of the annihilation operator. So certainly these e to the power I yes, alpha times e to the power minus I omega t also will be eigenstate of annihilation operator. So which you can just check it, okay, easily. So now if you do that, these will become the eigenstate of the annihilation operator. And what will be the eigenvalue? Certainly that you replace alpha by alpha e to the power minus I omega t. So eigenvalue, instead of alpha, it will be alpha e to the power minus I omega t. So we get the new equation, okay. So for the eigenvalue equations, okay, eigenvalue equations, where you can say that it is A operating on the eigenstate alpha e to the power minus I omega t will give you alpha e to the power minus I omega t alpha. The state becomes alpha e to the power minus I omega t. So we just got the time evolution of the alpha, and we saw that evolved state also a eigenstate of annihilation operator. That means this is also a coherent state. Now this evolved state is the same state. Just look at carefully. Just look at carefully. So what you see that these extra phase term which you got it e to the power minus I omega t, it is independent of this summation n. So it is like a universal phase, and if you multiply a universal phase with any quantum wave vector, okay, it will actually represent the same state. It doesn't have it, as you know that it ultimately what you have to do, that psi star psi. So you will get the same state back actually. So it will have a just multiplication of that global phase vector with alpha. So what we got it, time evolved state of alpha, okay, is the same state, and again it is the eigenstate of the annihilation operator. What does it mean? Means that we got a state alpha which is coherent over time. It is coherent over time. So that is the proof that if we can have the eigenstate of the annihilation operator, we could prove that will be coherent over time. So that's a quantum coherent state. So what would happen that it means that phase of alpha doesn't change over time, and we'll get the same alpha back, okay? And we can treat is a quasi-classical state. Why it is called quasi-classical state? That is because if you just now take the expectation value of the electric field operator, okay, with respect to this alpha t quasi-classical state, okay, what you will get, you can just check it, okay, you get the classical electric field, because now you have the propagation terms comes in, okay, so which was not there in alpha t. So ultimately you will get that your electric field, okay, classical electric field, monochromatic, definitely, isn't it? So that's why it represents the classical nature of the light, okay, in some short way or in some way, okay, and where actually it will become a classical state for particular kind of things, as you know that there is a coherent state available which is very popular, that is laser, okay, in classical sense. Okay. Is the laser is also can be treated as a quantum coherent state? That will be very valid questions. Okay. So we'll try to answer that. Okay. So let's see that. So what I'll just advise you, just maybe you can just do, work it out. This one, this to prove that expectation value of the electric field operator also give you that classical electric field, monochromatic. So far what we have learned. So we can drop the global phase for time being because that's not necessary as such. So we can say that we got the quantum coherent state, okay, which is the eigenstate of annihilation operator, and it will give the eigenvalue alpha. Alpha in the eigenstates, okay, looks like that it will be summation over the number of states. Now, come on. Now we have to understand what is the properties of this quantum state. That means, okay, we got a quantum state, okay. So now we were talking about in terms of electromagnetic field. So then how many number of photons are there in this state? Okay. That means can we say that something like an intensity of, which is associated with the quantum coherent state alpha? Okay. So for that what we have to do? We have to just take the expectation value of this number operator with respect to alpha. And if you do that number operator, which is nothing but a dagger A, and you know that the alpha is eigenstate of the annihilation operator A, which will give back the alpha back. And in the brass side, okay, what would happen? A dagger will be operating in the same way, but it will give the eigenvalue alpha star. So ultimately what you will get alpha star alpha, which is nothing but alpha square. So what you got that if you know the parameter that alpha for your quantum coherent state, you will be able to tell that what is the number of photons associated with that state. So that is give you the mean value, okay, of the number of photons in that coherent state. Now, so once you know the mean value of number, certainly you would like to know that does it have some kind of spread in that number, or it is a unique value? So if we want to calculate that the fluctuation of the number density, okay, or intensity measurement, if you say in another way, so what we have to do, we have to calculate the standard deviations, okay, or a square of the standard deviation variance. Okay, so if you calculate the standard deviation, okay, so it's nothing but you can use this formula that you can use that n square expectation value minus mean value of n square, okay, put the square root of this. And what I will advise you, just calculate it the way you have done it here, okay, and what you will get, standard deviation is alpha, modulus of alpha. That means variance is alpha square. The interesting point here that you see that mean and variance are same. And there is one kind of statistics which actually plays a role for this. That is the Poisson distribution. So what would happen that we'll also prove that, okay, that the kind of a number distribution of the photon inside that quantum coherent state, okay, will follow the Poisson distribution. Their population probability will be Poisson. How to prove that? You can do the simple way that try to find the m number of photon in that coherent state. So the probability of finding the m number of photon in the coherent state will be nothing but m of and overlapping m and alpha, okay, a square of quantities. And what you will find this expression, okay, as a function of alpha. And this is, you may not be able to recognize, but if I write it in this fashion, you will definitely recognize this expression where you put that mu equal to alpha square, modulus of alpha square, okay, then this comes out to be this format. And this is nothing but a Poisson distribution. So that means quantum coherent state is a state where the number of photons follows the Poissonian distribution. This is a theoretical proof, okay. Experimentally, it took a long time to prove, measure that really it follows this one. But people could get it for different kind of experiment. They have used it, okay. But definitely to prove that the Poisson distribution, I think there's a Nature paper in 2014, which actually definitely showed that the distribution is Poissonian. So what we have learned so far, that we got a quantum coherent state which behaves like a vacuum state, that minimum uncertain state. Also, its distribution of the photon in that system, in that coherent state, is a Poissonian distribution. So this is that thing is that you saw that the dispersion of the canonical conjugate operator, the Q and P, with respect to alpha is same again here, which is nothing but h cross by 2, as it was for the vacuum. And interestingly, what you see that if you just take that expectation value of this Q operator, okay, you will get that real value of the alpha. And once you take the expectation value of P with respect to alpha, you will get imaginary value of alpha with a prefactor. So what you get that what you realize earlier also, that imaginary and real values, okay, you could show that is can be related to the Q and P. Here also is true. Okay. So in vacuum we have shown it as true. So I advise you to just work it out with some small calculation derivations, which will help you in the long run. So once you have realized, okay, that population probability satisfies in the coherence to satisfy the Poisson distribution. Now, if you just take that the spread or dispersion over the mean intensity, okay, so that means that you are taking that standard deviation values over the mean values. What you see that this is going by alpha and this is going by alpha square, so it is 1 upon alpha. And for a large value of alpha, this will be for a large value of alpha. Okay, what would happen that this will give it very narrow width. So once you increase the number of or increase the value of alpha, okay, once you consider alpha values large, okay, then what would happen? You will get much better in terms of the narrowing down the dispersion. The coherence will be much better. Okay. So that alpha value dictates, okay, in the coherent state, that how good your coherent state. Okay. So the more number of photons, the alpha value, as you say, that it actually tells that how many number of photons are there. Okay. So if you have a more number of photons in the system, because alpha we are writing in terms of summation of a number state. So if you have the more number of photon, okay, that this summation will be dominated by the number of states which are having more, okay, number of photon. So that if you have the alpha state where alpha value is large, okay, that means that though these are dominated by the large number of photon, okay, it will be better, it will give the better representation of the quantum coherent state and as a quasi-classical state. Okay. So once you have that alpha value is large, as I showed in the graph also, okay, how it is be almost close to like a classical nature of the coherent state, okay. So if you just see that the Poisson distribution, if you increase the value of alpha, which was there like alpha equal to 1, this one, if you increase, what would we turn out to be like a Gaussian, okay, like a classical light, okay. So classical Gaussian laser light, okay. So ultimately what you see that if you have a quantum coherent state having large value of alpha, it will represent the laser, classical laser light. Or classical light, other way to say that, can be also understood as a quantum coherent state, having the Poisson distribution. So that's very good because now we have something which is classical also can be used. Okay, that's a big advantage. And also, as I said that in this case, the dispersion will be minimum, okay, as the vacuum state. So we have now a state where you have a large number of photons available. Also, it behaves like a vacuum. So minimum dispersion. So nothing more we can ask for. Okay. So we are now free to do experiment with this. So that's things which we understood so far. So we got the quantum coherent states, okay, as good as the vacuum states. Now, so same repetition. Okay, let me see that in terms of phase space. So if I just want to plot the in terms of the canonical conjugate, canonically conjugate operators Q and P, and draw the spread of the states, okay, that standard deviation, okay. So what would happen? Vacuum state, as you know, that standard deviation with respect to the vacuum state, the Q value is same as the P values, okay. So that is square root of h cross by 2. So we expect that there will be circular disks around the center of the coordinate system in the QP, PQ coordinate. Okay. What would happen this one? So this one also will be the similar kind of a spread. So we'll expect that this is also, okay, having the circular disks in terms of the fluctuations. Okay, in terms of fluctuation, this is also similar kind of in the direction of P and Q. It will be minimum. Okay, and there is the same values. Now, as you see that I have drawn it in the somewhere else in the phase space. That's because there is something, some feature that this coherent state has alpha, so that I had to place it somewhere here. That's because that if you take the expectation value, okay, of Q with respect to the alpha, it will not give the 0. Unlike that vacuum state it was 0. Okay, so that means this is a finite value depending upon the value of alpha. So it is nothing but real values. So if I just go in that axis, okay, this will be that real value of alpha with a factor of square root of 2h cross. Similarly, if we just take expectation value of P with respect to alpha, it will be imaginary value of alpha. So if you go in this axis, the vertical axis, where P is there, okay, you will get this will be representing the imaginary value of alpha. So altogether, what we'll see that if you just want to place your alpha in this phase space, it will be nothing but somewhere where actually this will be the coordinate for the real value and imaginary value of alpha. So it will be somewhere here. So what we see that by changing the value of alpha, I can get different value of real alpha and defined value of imaginary value of alpha. Okay, so I'll be able to put these disks anywhere in the field space. So that means that these coherent states, okay, actually representing the defined points in the field space, that PQ field space. Okay. So if you choose any particular point from the field space, that corresponding to that parameter, okay, if you create that coherent state, okay, so that will be the state which will represent that minimum uncertain state. Okay. So this is the things which actually proposed and proved mathematically by Ray Glover. And because of that, after his actually experimental demonstrations, he got a Nobel Prize in 2005. So now we have two very good state. One is the vacuum state, and another quantum coherent state, which actually in our exploitation to choose what value of alpha we want. So we have a very good degrees of freedom to choose the quantum coherent state. It also means that if you choose alpha value is 0, you get the vacuum. So vacuum is also a quantum coherent state. Please don't forget that. But by choosing not equal to 0, I'll get anywhere else in the field space. Now, question is that, is it possible to transform the vacuum state to that any non-zero alpha value state? Or we can reverse it. So if you know that the quantum coherent state for alpha not equal to 0, can we just go back to vacuum state? So that is a valid question. Okay. So is there any way to transform one to another? So that is a transformation rules available. Mathematically you can show, and experimentally later we will show that how it is possible after we discuss the beam splitter. But let's discuss today the mathematical approach. Okay, that this is a operator, as we expect, that which you operate on the vacuum state. We want that quantum coherent state alpha or alpha not equal to 0. So that operator, okay, I am naming it displacement. Okay, I mean it is told a displacement operator, and there is justification for that. Okay, as you understood actually in some intuitive sense that, okay, that it is displaced the vacuum state in the field space from here to at the point where alpha is there. Okay. So at least you understood that there is some kind of displacement happening, and we'll try to show that in that derivation that yeah, really there is a displacement. Okay, so now if we have this displacement operator, how it looks like. So in our knowledge, we have the value of the alpha. So that we have to keep it in mind. Can we use that? Yes, we can use that. As we understood that this alpha is nothing but a linear superposition of the number states. So if you want to create the defined number states having the defined number of photons, that means that on the vacuum state, you are operating defined number of creation of operator, so that you will be able to generate the defined number state having defined number of photons. I hope I'm clear in that. So what would happen that since there is summation over n and this is a number state, okay, so that means to create these number states, I need to operate that d alpha should have something like that, a dagger with its different power, so that I can get n. This is exactly done. And since n goes to 0 to infinity, there's one way we can do it using exponential. So if you use that alpha a dagger, which will give the different powers of a dagger with the coefficient alpha, okay, we are done. But we have to be unitary in the sense that d alpha should be unitary. So to make it unitary, we have to add, we have to factor with the e to the minus alpha star a. And to make it in a form, coordinative form, we have to have a prefactor of this e to the minus alpha square by 2. So altogether, if you look at it, it is like a unitary operator, e to the alpha a dagger minus alpha star a dagger. So the exponent, what you see, it's nothing but a Hermitian operator. So if your exponential of Hermitian operator will be a unitary, isn't it? So that means that what you got it, that you got a unitary operator operating on the vacuum state, which we take you to the quantum state, where we have used that commutative relation between A and A dash. Yes, there's a question, something? Some noise is there? Okay, thank you. Thank you.
I think nothing, Professor, you continue.
Okay, fine, thank you. So once you have this displacement operator, which actually help you to take that vacuum state to or the quantum state, depending upon which value of alpha you choose. Okay. So, so we want to address the question which you initially told. What is displaced? So we are telling it the displacement operator. What is displaced? So for that, what we have to just consider, okay, that take that alpha in terms of its real and imaginary values. Okay. So if I say that x, small x is the real component, value of the alpha, or real component of alpha, small p is the imaginary component of alpha. Okay, and we can write alpha is in this format. And similarly, we can write that Hermitian operator, which is non-Hermitian, in terms of the Q and P Hermitian operators. Okay, so here you just keep in mind that H cross is 1. So what we can write, okay, we can write that the displacement operator, which is d alpha, is nothing but you just put all of them e to the power minus I x p hat minus I q I p q hat. So x is nothing but, remember that the real part of this alpha, p is imaginary part of the alpha. Okay. And these are the operators. So what you can show that, as we saw it in the last derivation, that we could break up this expression in terms of the different exponential format. And you saw that in particular exponential factor, you have that operator P and another it is operator Q. Okay, so the operator which is having P, we are let me write it. This is dx0, and the operator where it is Q, like GP, dpg, 0p. What it works? Let's see. So what you can prove easily that this exponential of ix p hat by h cross, which is a factor of here, okay, if you operate on any eigenvector, any state vector having that position as one of the argument, okay, what would happen? It will nothing but that translate that state, okay, to some extent by governing by that amount small x. Okay. So that translation will happen. So it will be translated in the position space. So that this operator give you that translation, displacement in the position space. Whereas the this operator d0p will give you, this is nothing but your IPQ hat by h cos, okay, operator psi, it will give you a phase that means that it will be displacing in the imaginary directions. Okay, the phase means that in imaginary directions. So it will give you a effect. So ultimately, which you can work it out, that d alpha, what you see that is nothing but a translation in the position and momentum space by amount x and p. So that's why it's called displacement operator. And we could easily develop this in the experiment where actually you see that suppose you have this kind of a string, okay, the function which is spread like a sinusoidal kind of this. Now if you operate the dp minus x, okay, you want to shrink this, so what you see that string, okay, the oscillation of this or distribution of the effects will be synced. Okay. So it will be sorted by capital X amount. Similarly, so this can be experimentally also can be demonstrated. Think about that light is propagating through the fiber. And if you can make the fiber having some kind of loops here, what you will be done actually, you are nothing but using the displacement operator in minus X, in the position space minus X. So by using the different loops, you will be able to achieve that. Similarly, if you have a distribution of function, okay, or X like that with a period, let's say twice pi by k naught, okay. So what would happen that if you just operate a dxk, that means you want to shrink that period, okay, by the amount of capital K. So that is the way we understand the displacement operator. So it actually displaces in the position direction or also in the momentum directions. So just maybe the last two slides, okay. So once we understand the displacement operator, its action, it takes that vacuum state to the quantum coherent state, okay. So what other property it can have? So certainly it can come to a mind, if I do, instead of that single displacement, two displacement, what would happen? Three displacement, what would happen? Okay. So is it that if I do the two displacement, okay, that one by alpha, another by beta amount is same as that displacement by alpha plus beta? So to prove that you just check that d of alpha beta, which you can write as we have factorize it in terms of different exponent. You have to do it here also, okay. What you will see that you will be able to do, okay, you will be able to write d alpha plus beta is nothing but d alpha times d beta is one operation after the another operation, okay, but you will have to adjust with some phase, okay. That phase is nothing but exponential I beta star minus alpha star beta by 2, which is nothing but imaginary quantity of alpha beta star, okay. So you have to adjust the extra phase if you want to do sequential displacement and also want to get in a single displacement. So if you want to compare that, you are going this one and alpha amount, this one is beta amount, and you want to get the same by the alpha plus beta amount, you will not be able to get the same thing. Apart from that, the extra phase is there. And this phase is the imaginary quantities. And those who are mathematical minded, these actually form the Heisenberg-Wiles group, okay. So this phase, extra phase, which also called that displacement composition phase, okay. So this is actually, we got it because we are doing the sequential displacement one after another, okay. So this is the paper, very good papers, which you can look at it, European Journal of Physics, okay, 2018, where this is discussed, okay. So we actually gain a phase after doing the sequential displacement, okay. Now there's the interesting things, okay. So once you do this, once you gain that sequential, gain a phase by doing the sequential displacement. So if I think that okay, I just displace this amount, beta amount, then some other amount, and let us come back to this original position. What would happen? Just imagine something which you have learned from the Berry's phase, okay, something Arnav bomb effect, okay. So can we have the similar kind of things? Yes, we can have it, okay. So let's see this example which is given in this paper. This is a very interesting paper. Okay, so you start from the A position, go to the B position by displacing this, okay, in the X direction, okay. So you use that Hamiltonian for that displacement. You gain the phase, okay. Then you just displace in the momentum directions, go to C, then come back to D, and then finally you come back to A, okay. So you make a loop. So A to B to C to D to A. So what would happen that if you see that at each step how much phase you gain by one after another, it is, you can just see that it is nothing but that exponential I, your what do you call that, S times H cross, okay, action, sorry, action time by H cross, okay. So this is your action. So action, okay, what you can write in terms of Lagrangian, okay, or which you can write in terms of Hamiltonian. So if you write action in terms of the Hamiltonian, is nothing but integration of p dx minus Hamiltonian for particular translation, transformation, okay, times dt. So here, like here, this is H1, this is H2, this is H3, this is H4. So this P naught X minus P naught cap. So that is a two. This is that from capital X naught, capital P naught to capital X naught plus X plus. So you just have to see that how much will be the Hamiltonian for displacement operator. Okay, so you just calculate that Hamiltonian. This is your Hamiltonian, and you calculate the action. And if you put it in your exponent, what you will get? The phase. So you accumulate the phases for all this displacement and get back, and what you will find that is nothing but that what you got it, that amount of the surface you covered by displacing this one is coming out to be the phase in the unit of h cross. So this is nothing but x times p. Okay, that is the rectangle area of the rectangle which you covered. Okay. So that much phase you occurred. So that is like similar like that Berry's phase kind of things. Okay. So this is can be described as the displacement composition phase. Okay, this is due to the displacement. So what we got it. Okay, this is a nice example which you saw. So we saw that displacement operator. Okay, its properties. So the one of the properties, as we mentioned, that it was required that it has to be your unitary. Okay, so that means that your d dagger alpha will be nothing but d inverse alpha, or you can get the same expression of the d inverse by replacing alpha by minus alpha because it is in the exponent. Okay. So the interesting point is some of the things which I forgot to mention earlier about the coherent state. The coherent state here is actually, as you saw, that it is normalized. Okay, but thing is that if you take the different coherent state alpha and beta, you see that it come out to be e to the power minus alpha minus beta square. Unless alpha and beta are same, there's no, but they're same. Okay, there's no way you make it one. So that alpha and beta same means that it is one, and that is actually we have seen that. But point is that if alpha not equal to beta, it is not zero. Unless either alpha or beta is very large. One of them has to be very large. So that minus of this the exponent, it will make it close to the zero. So these kind of coherent states, okay, which actually normalized, but it's not that orthogonal, okay, but you can make it orthogonal by choosing the different parameters of alpha, okay. So this is known as over complete basis. So this will not be from a normal complete basis, but it is an over complete basis. And another thing what actually we can find out that from the coherent state, okay, that now what you can see that from the definition of the coherent state, what you saw that the annihilation operator acting on alpha will give alpha alpha. So now we can replace alpha by d alpha operating on zero. So using that, what you can get easily that if you operate d dagger alpha from the left hand side, okay, so it will be up, you will get able to see that the transformation relation, okay, of this d alpha on the annihilation operator. So d dagger alpha, a annihilation operator, and d alpha operating on zero will give you alpha. So that means that your annihilation operator will be actually displaced by some amount. Okay. So what you can show that if you put that the alpha, this operator, so since A is operating on the zero is zero, okay, I can see that A operator will be displaced by alpha amount. Similarly, annihilation operator will be displaced by the alpha star amount. Okay. So if you just operate in a reverse way, okay, that will be giving you negative direction of the alpha. So what actually in terms of the canonically conjugate operators, which are actually Hermitian, okay, for the Q, okay, as we have seen that also that this is nothing but a displacing in the Q direction, okay. It was already shown in the derivation, okay. So you can see in terms of operator, okay, in terms of Q and P operator, okay. So just the last point which I want to address it here. Once we got this one, that defined displaced state, okay, like we have got a basis from the Fock state, can we get a basis in that displaced Fock space? Okay, so what we see it here, we got actually we will be able to operate at d alpha on these Fock states, number states, and it will be again what you can prove that they'll be orthogonal to each other. Okay, and these will be again forming you another complete basis. Okay, as you got it from the Fock states. So this is interestingly this is called this displaced Fock space. So what we have, so I want to conclude here. So what we have learned so far, we have learned that once we quantize the light, okay, we got the number states. Using those number state of Fock state, we could construct the state, okay, which is similar like a vacuum state, which is minimum dispersive in nature, okay, but it can contain that any number of photons depending upon our choice. If you choose number of photons large, this will be giving you something close to our classical laser light. Okay, and you will be also able to get this quantum coherent state by using the displacement operator. So if you operate displacement operator on the vacuum state, you will get the quantum coherent state, and this displacement operator should be dependent on the parameter of the coherent state which you like to get. So we'll discuss how to construct experimentally how to construct the displacement operator in next class, after we discuss something which is very, very unique in the quantum optics, that is the quantum beam splitter. So quantum beam splitter, which we have to learn, understand very well to do any kind of experiment. This is like any fundamental particle in a particle physics. This is also very fundamental, which you have learned, and then we'll discuss that how to develop the displacement operator in experiment. And subsequently, and then I think day after tomorrow we'll go to the squeeze state. Thank you for your attention. I'd love to have some questions. Though I watched your time, sorry.
Thank you, Sanjay, for such a nice session today. So let me pass on some questions from our audience. So the first question is every eigenstate a coherent state, as eigenstate don't change with time?
Every eigenstate of annihilation operator is a coherent state, right? Every eigenstate of the coherent, annihilation operator is a coherent state. That's, you are right. So as you see that we can get it by changing the parameter alpha. Okay, so that is the only way we can get it.
The next question is how is alpha a quasi-classical state, since it was a superposition of many quantum eigenstates?
Right. So as we have proved it also that if you would take that expectation value of the electric field operator with respect to the alpha t, what you saw, you get the classical electromagnetic wave, which is monochromatic in nature. Okay, so that is one way to prove that. Also, we saw intuitively, at least from the point of view of the summation which you have used for defining the quantum coherent state alpha in terms of the number state. If you just think about that number of photon is very large in a particular state, okay, so in the quantum coherent state, okay, so that means that when you write alpha in terms of summation about the number state, in the summation the coefficients which actually tell you what is the weightage of the number state or to give that quantum coherent state, okay, and what you see that because there is a dominancy of the large number state now, due to the large number of photon availability in the system, okay, what would happen? It will behave like a laser light. As I showed that if alpha is large, it will become a Gaussian nature, okay, and the Gaussian nature lights, okay, you can tell that is a like a classical light, okay, like a laser light, okay, which has the peak at the center, and then there will be the decaying intensity feature, okay, as we gradually go away from the center, okay. So that actually shows that, okay, yeah, really that that quantum coherent state can mimic, okay, the classical light when you have large number of photons. There's a laser light. But anyhow, in theoretically also you can prove, as I showed, that from the expectation value of the electric field operator with respect to the alpha, okay, you could get that electric field itself, which is propagating and monochromatic in nature. So if you do it for the multiple modes, you'll get the different value of the omega also, different omega also. Yeah.
Okay, so the next is actually why the eigenstate of annihilation operator changes with time. Is it because annihilation operator is not Hermitian? What does it mean physically?
Okay, so I didn't understand the question thoroughly.
Again, I'm repeating, sir. Why the eigenstates?
I heard the question properly, but I didn't understand in the sense that if you have any system, okay, and if you keep it over time in a space, and either in a room somewhere in some ambience, okay, it will evolve, isn't it? It will interact with the ambience and evolve. If you keep it in an isolated space, okay, so it will just evolve like the way Schrodinger has prescribed, okay, that it will be by minus IHT by H cross, okay. So it's a unitary evolution. So here what is happening, what actually I think what he wants to say, that when you just keep it, okay, inside a small space, okay, which you describe to quantize the light, okay. So in that space, if you can make it isolated, okay, and what would happen that your different number states will evolve with time, okay. That's because you want to see it after some time. Okay, the number state when it evolves, okay, since their number of photons are not changing, okay, they will be evolving unitarily, and if you sum them up, you will get the total evolution of the quantum coherent state. Okay, so you just have to look at it after different time, and what you see that here, what is happening? It's not changing. Quantum coherent state is not changing. Okay, so that's why it's called coherent.
So there is one associated question also. If we try to measure a quantum coherent state, will there be a finite probability of arriving at another coherent state?
Means what? I mean, it depends upon what actually you want to measure. You want to have a number of photons. So see here what happened. So if you saw that if you want to measure number of photons in the quantum coherent state, as you see that mean value will be alpha square, okay, depending upon the parameter alpha which you complex value alpha you choose, okay. But you see that there is a spread, okay, so that spread will be there, but you will not get beyond the spread, okay. That's the important part, that spread, what we say, that a minimum dispersion, okay. So that you have to bear with. Apart from that, you will not get any arbitrary value of alpha, arbitrary value of number of photons. Okay, so that's the beauty of the quantum coherent state. That if you choose that quantum coherent state, your number of photons is almost fixed. Okay, so there is small dispersion from the mean value. Okay, so that is one point. Similarly, if you see that if you want to find out measure the position of the state, okay, there also you saw dispersion is very small. That it depends upon the real value of the alpha. Okay, how much you took. So if you have taken that alpha is large, okay, then if you measure the position, as the real value of alpha will be very large, okay, because alpha you have chosen large, okay, so there will be a spread, okay. But if you choose that alpha is small, okay, the spread will be narrowing down. So depending upon your choice of alpha, So if you choose that alpha is large, like with the classical laser light, where your number of photons are very large, okay, that means that speed of the Q, the position operator, will be large. Similarly, you can talk about the momentum. So that is the way you can define it.
So there are two questions which looks similar, so I'll state both of them together. One is, how can we increase value of alpha practically in laboratory to get classical laser light? And then another one is again related to experiments. Our classical and quantum lights are different in experiments, how we can basically show that this is classical through some experiment.
Okay, so very good question. So that is an experimental point of view. So the thing is that, okay, the one way to look at it, that if you take the laser anyhow, that number of photons is very large there, okay. But now let us consider that we are confined the electric field, okay, inside the small space. Now, if you consider that space is very small, okay, then what you can think about that, depending upon that, the strength of the electric field, the amplitude of the electric field, your population of the number of photons will be decided. So, and what will be the energy gap between the number of states? That will be decided by the volume, the length, okay, or width. Okay. So once you have the fixed volume, you know that a different number of states are defined at particular energy levels. Okay. Now, depending upon the amplitude, which number state will dominate for that system, that will be decided by the amplitude of the electric field which you confine in the systems. If you can confine that very strong electric field, certainly that will have more number of photons. That means that the higher number of states will be dominating for the system. And if you have the very weak electric field, it will be dominated by the lower n values of the number of state, okay, which actually having the low number of photons. So it depends upon what strength of the electric field you confine in the small volume. So that I think you have to control it by some means, okay, by using pump or using some kind of an approach, okay, where you can just change the amplitude of the electric field. So that's that.
In the same, I have a question, like, let's say if we have some profile, we measure the profile of the light, and then by fitting the profile, can we state something? Because we know that, let's say in some laser, or we will have a definite Poisson distribution or Gaussian distribution. Through that, can we state something?
Yeah, that. So mostly, when you the classical laser light, which is coherent, okay. So what you see that this is Gaussian nature in the intensity profile, okay. And as I showed that Gaussian nature is one kind of a Poissonian if you have the large value of the alpha, mean value, okay, mean value of the distribution. If you have a mean value of distribution large, okay, you can make it, okay. So what you can see that from the profile itself, if you see the Gaussian nature, okay, and so you can tell that if that is coherent, okay, that is have to be in the classical nature, in classically coherent, then you can say that this is can be also used as a quantum coherent state. Okay. And if you see the Poissonian distribution, definitely for very low number of photons, okay, if you see that light which is strength-wise very low, okay, if you see the intensity profile and see that it has a Poissonian profile, then definitely you can say that that has a quantum nature. It would be more ideal to do experiment in quantum optics, okay, if you go below that Poissonian, sub-Poissonian kind of distribution, which I'll discuss when I talk about the statistics part of the light, okay. Those will be like single photon, two photon, multiple photon number of photons, which if you use for your experiment, then you are sure that you are in the quantum distance of the light. Okay, so you will be able to that time just dealing with the quantum mechanics, quantum phenomena. So that you will be confined.
Okay. So one last question we'll take for this session. What are the implications of having an over-complete basis?
There is no application. The application as such, and it is the advantage, or if there is a feature it has. Okay. So the feature it has, that this is that way we could get it. Okay. The way we define it. Because see that we are actually able to write any states in terms of we will be able to write in terms of this coherent state. Okay. But as you see that alpha can be any value. It's a infinite number of values. So what would happen that you will not be able to exhaust. Okay. Since there is no way you can. So if you, even if you take a small dimension of the span of the scalar values, okay, or in the real space, if you take small span, okay, so maybe 0 to 1, there also you have infinite numbers of real values, okay. So, and for each value of alpha, you will get coherent state. So if you just integrate it, so you will get the completeness, okay. You can use that as a basis. Ultimate idea is to whether can I use this alpha as a basis or not. That is the completeness question comes. So you can use it as a basis to some extent. Okay. So it is, I mean, in a conventional that way we use a basis for a complete number of set. Okay, complete set. That is not true here, but you can use as a basis. But it is a continuous basis.
So with this, I thank you again, Sanjay, for such a nice session in the morning. And I think participant will have more time to discuss things during tutorial session as well. So with this, I would like to ask Professor Deshmukh to please conclude this session.
Yeah, thank you very much, Ritesh. We had a very lively question answer session as well, following a brilliant lecture as always. Sanjay, just one query, very informal. You talked about global vectors.
Right.
So would you like to comment on Sudarshan's contribution to this? Because he did not get sufficient credit for this, and you know it's always called as global vector.
Yeah, the last question which was asked actually over completeness.
Yes.
Okay, it was addressed to that. Okay.
Yes.
So so maybe I'm not. I think
maybe sometime
Okay.
you may want later you may want to comment on that, because I think it is good for people to know about Sudarshan's work.
Definitely in the beginning of the next class, I think
Yes.
I'll discuss and then proceed.
Yes, because he made very valuable contribution, and a lot of people even think that he should have been included in the Nobel citation. So anyway, brilliant talk once again, and I see that.
And the contribution. So one more thing, there is a contribution from the Professor G.S. Agarwal also in that.
Yes, yes, absolutely. Yes.
He has told that you can make the eigenstate of creation operator instead of the annihilation operator also.
Yes, yes.
So there are a lot of works. Okay.
Yeah, there has been some other important contributions. I think that Ashit Barik was raising his hand. I do not know if he had a question or something that we missed. But if we did, then maybe I will request him to send an email or let us know so that we can follow up on that next time.
Oh.
So other than that, I think we are pretty much ready to close this morning session. So thanks to...
We will have a tutorial in the evening.
Yes, and we are meeting at 3 o'clock, Sanjay?
3 o'clock.
Yeah, so we all meet at 3 o'clock this afternoon. Looking forward to that. And as always, the technical support from Arun, Sairam, Ravi, Devi, Prashanti, you know, everybody is superb, which is why we are able to bring these lectures to all of you. So thank you all very much, and we will meet at the tutorial this afternoon.
Thank you very much.
Goodbye for now.
Goodbye.